afternoon. Today we're going to do a new unit on sequences and series. I want to first just talk about some of the purposes of why these are useful, how they're used. Second, I'm going to go through some formulae for how they're written, both sequences and series. And then we're going to do some tools which we'll later use for sequences and series, which are factorials and summation notation. So write those down in your notes. I'm going to start with what is a sequence or a series. First of all, and you should look at your notes for these as well, a sequence is just an ordered list of numbers. Let me give you an example. You've been doing this for a while. There we go. 1, 3, 5, 7. I think most of you would know the next one is 9, 11. Basically, you're going up by 2 every time. That is a sequence. Some notation for that. Each one of these elements is called a term of the sequence, just a term. So this is the first term, that's the second term, that's the third term, that's the fourth term. The other notation we use generally is this. You use A for the terms. So you go A1, A2, A3, A4, etc. So this is the first term, it's listed as A1, this is the second term, A2, the third term, A3, the third term, A4. If you add these up, for example, A1 plus A2 plus A3 plus A4 plus this is called a series. So again, a sequence is a comma-separated list of numbers. Each element is called a term. A series is simply the summation of that sequence. Okay, so let me go through the uses of this. They're used for a number of things. The first one is to define constants. For example, you may have wondered, and I talked about this in geometry, how do you know that pi is 3.1415, etc.? And how can they get the millionth digit of this? The way you can do that is by using what's called an infinite series. Pi is actually the summation of 3 plus 4 over 2 times 3 times 4 plus 4, oops, that's minus 4 over 4 times 5 times 6 plus 4 over 6 times 7 times 8 minus 4 over 8 times 9 times 10, etc. So you can see there's a pattern to this. So all 4s across the top. It alternates positive and negative. Then it goes 2, 3, 4, 4, 5, 6, 6, 7, 8, 8, 9, 10. If you add these up, you will get pi. And it goes on infinitely, so if you want a millionth digit of pi, you just have to do many, many, many terms of this. There are similar ones for e, for example. E is simply 1 plus 1 over 1 factorial. We'll get to this notation later. Plus 1 over 2 factorial, plus 1 over 3 factorial, etc. That's how you get many of these constants. That's the first use of it, just constants. Second use is to come up with ways for your calculator to calculate actually these functions. For example, if I wanted to calculate, say, e to the 1.2, you can just put that in your calculator, but how does your calculator do it? What your calculator does, largely for all of these functions, is it uses infinite series. E to the x is 1 plus x over 1 factorial, plus, that's for x the first, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus dot dot dot. So all I have to do, if I want to do e to the 1.2, is put 1.2 in there, 1.2 in there, 1.2 there, and do it to enough points where I get enough decimal points, and then the calculator just displays it. Same thing with, for example, sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. It goes on forever. If I want to do the sine, say, of 20 degrees, well, actually, first of all, it doesn't take it. It's not. It has to be put into radians, but the equivalent radian equivalent to 20 degrees. You put that in here, 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 and here. Calculate it and give you sine of that 20 degrees. So this is how your calculator actually does functions. That's the second way of doing it. Third function or purpose of sequence and series is simplifying physics equations. So that infinite series I had before had sine of x equals x plus blah, blah, blah. These terms, which I think was x cubed, let me go back, so it should be minus, let me do it another couple terms, minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, dot, dot. If x is small, these terms are really, really tiny relative to that one, and you can just cancel them out and approximate sine x, for example, as x. And this, putting x in instead of sine x, makes largely unsolvable physics equations solvable. Okay, the final application is what we're largely going to do in this class, which is just a few geometric and algebraic problems that you can use and solve with arithmetic and geometric sequences. But they're actually not the most useful ones. It's more just done for an introduction because they're more straightforward. Okay, so now we're going to do for the formula. I'm going to write this at the top. Sequence and series formula. These are the equations which we use to generate the series and sequences. So let me just give a couple definitions first. A sequence, as I said, is just an ordered list of numbers. They can be either finite, meaning they end, or infinite, meaning they don't end. Let me give you some examples. 5, 10, 15, 20, 25, 49, 43, 37, 31, 25. Let's just put those there. What I want you to do is pause the video here and give me the next 3 terms of both these sequences. I think you can probably see those. And when you finish, come back and unpause it. Okay, so the next ones in these series are 30, 35, 40. Basically, I'm moving it by 5, and this one I'm dropping by 6 every time. Minus 6, minus 6, minus 6. The next one is 19, and then 13, and then finally 7. Okay, and it keeps going. So if this is finite, I'm just going to stop at some point. Like, let's just say I stopped here. And I've got this sequence of 1, 2, 3, 4, 5, 6, 7, 8 numbers. If it's infinite, I just say dot, dot, dot. It doesn't end, it keeps going. So I can keep going with this, subtract 6 again, get 1, etc. That's an infinite series. Finite means it stops. Okay, now I'm going to give you a couple ways to write formulas for these, both the finite and infinite. There are 2 types of formulae for it. There are what are called the explicit formula, which allows me to get any term in a sequence or series just from the equation. And I'll give you an example of that. A of k equals k squared minus 1. What this means is I can get any term in the sequence. Like if I wanted 2, a2, I could just put 2 in here. So let me do a few. a1, I just put a of 1. I put 1 over here. This is 1 squared minus 1, or 0. a2 is 2 squared minus 1, or 3. a3 is 3 squared minus 1, or 8, etc. So all I need is this formula, and I can generate these terms. This is called, as I said, explicit formula. And now there's another type, which is called the recursive formula, which is actually more how you actually think about sequences generally. For example, 1, 2, 3, 4, 5, 6. Actually, it's 4. You better want to do this one we had originally. 1, 3, 5, 7, 9. This one, how do you get from one to the next? You just add 2. So how do I get the next one? I add 2 to the previous one. And then I add 2 to the previous one. And at no point do I have an actual formula where I'm saying, hey, this is the 1, 2, 3, 4, 5, 6, 7th term. If I put some number in 7 in some place in some formula, I'll get 13. That's not what I'm doing. I'm just adding 2 every time. So let me give you an example of that, how you write that. So I could write the first term is 3, and the next term, which I'm just going to call a to the n, sometimes a to the k is written, equals a to the n minus 1 plus 2. So what this is exactly what I had before, so I'm starting at 3 here. So what this means is the first term is 3, the next term, if I want to find A2, so let's do this right down here. A1 is 3, because I was told so. That's where I'm going to start. A2 is A1 plus 2. So I put 2 in here. This is 2 minus 1, which is 1, plus 2. And that just means I take the previous term, which is 3, and I add 2, and I get 5. And then if I want to do A3, A3 is simply A3 minus 1, or A2 plus 2. And A2 is 5, so it's just 5 plus 2, and it's 7. So this is what we were doing before. It's a way of just adding 2 to the previous term. To do this, so again, two formulas, the explicit formula, which will allow you to say find the 100th term just by putting 100 in there. In this case, it would be 100 squared minus 1. Or I can have a recursive formula, which is harder to find like the 100th term, because if I have this equation, I have to get the 100th term, I have to find the previous 99. But it also is more like how you think, which is you take the first term, you add or do something to it, multiply, subtract a number to it, and get the next one, the next one, and the next one. Again, this is called explicit. This is called recursive. Recursive means it circles back on itself. It's using its own numbers. Okay, let me give you some examples to work through as problems, whiteboard problems on this. So first I've got a formula, a to the n equals 3n plus 2. This is an explicit formula. I know that because it doesn't have a first term. And over here it doesn't have a to the something, it just says n itself. So sometimes these are used as n, sometimes as k. Okay, so I want you to do is list the first 4 terms. Okay, pause the video, list the first 4 terms. Okay, if you're back, A1 is simply 3 times 1 plus 2, or 5. A2 is 3 times 2, which is 6, plus 2 is 8. A3 equals, put 3 in there, 9 plus 2 is 11. A4 is 12 plus 2 is 14. So 5, 8, 11, 14. You can see what we're actually doing is adding 3, which is, by the way, is that 3 there. But at no point do I actually, I could write this as a recursive formula now. I could say A1 is 5, and my next term is simply the previous one plus 3. That would be the way to write it recursively. But anyway, here was the answer to your question, the question I was asking. Let me do another one. A to the n equals 1/3 to the n. Okay, well, again, write the first 4 terms. Okay, pause it. Okay, now here are the first 4 terms. A1 is simply 1/3 to the first, which is 1. A2 is 1/3 squared, which is 1/9. A3 equals 1/3 cubed, which is 1/27th. And a to the 4th equals 1/3 to the 4th, which is 1/81st. Again, I could write this as a recursive formula, though it's not as obvious, but it is. But I have to write the first term, it's 1/3. And the next term is simply the previous term times 1/3. That's how I go from one to the next. 1/3 times a third is a 9th, times a third is a 27th, times a third is 1/81st. Okay, we'll do one more on the boards. This time I'm going to give you a recursive one. A1 equals 7, a to the n equals a to the n minus 1 plus 5. And write the first 4 terms again. Okay, pause it there. Okay, you're back. First term is 7, because I said so. And then I'm just adding 5 each time, that's what that says. So the second term is the first term plus 5, which is 12. The third term is the second term plus 5, which is 17. The fourth term is the third term plus 5, which is 22. There we go. All right, we're going to do one more. Here's one. This is actually from the pre-calculus material, but I'm sure people in Algebra 1 could do it as well. This is my explicit formula. Again, I know it's explicit because there's not an a to the n minus 1 over here or anything like that. It's just in terms of the number. I can put in the 5th term and just put 5 plus 1 over 5. So give me the first 5 terms. In this case, pause the video. Okay, so let's go through it. A 1, put 1 in there, and you get 1 plus 1, 2 over 1, or 2. A 2 is 2 plus 1 over 2, or 3 halves. A 3 is 3 plus 1 over 3, or 4 thirds. A 4 is 4 plus 1 over 4, or 5 fourths. And A 5 is 5 plus 1 over 5, or 6 fifths, etc. I just want the first 5 terms. Okay, that's how you use the formula. This one in this case is explicit, or the recursive one, which just calls back on itself. You can tell the explicit ones have only n on this side. The recursive ones will have a to the n over here, and a to the n minus 1, maybe even a to the n minus 2 over on the other side. Okay, now we're going to do series definitions. So as I said, I think I mentioned this in the front, but let me give a formal definition. A series is a sum of a sequence, basically just adding it up. Series can also be either finite or infinite. Well, if they're infinite, they actually have to, in order to have a value to sum it up, they have to actually shrink in value over time. So let me give examples of that. I had this one before, 5, 10, 15, 20, 25. That was a sequence. If I want a series, I just get rid of these commas, and I add them. And clearly, from a finite perspective, that has a value. You could add them up. 5 plus 10 is 15, plus 15 is 30, plus 20 is 50, plus 25 is 75. So you are actually adding them up, not just writing them like this. You have to add them up. Let me give you another example. 1/2, plus 1/4, plus 1/8, plus 1/16, plus blah, blah, blah. This one is an infinite series. And it looks like it wouldn't have a value because it goes on forever, but it actually does. We'll talk about that later. Actually, on another lesson, I think. But this is actually just equal to 1. If you add this in a calculator, you can try this. Just keep adding these numbers up and get closer and closer and closer to 1. We'll never reach there unless you wrote an infinite number of numbers down, but it gets very close. This idea of a series that converges, basically, or gets to a number, actually has a name. So for infinite series and sequences, infinite series, if it approaches a number, that should be a number, it is called converging, or it converges. It converges to a number, in this case 1. If it grows forever, in other words, this one's shrinking down, this one's actually getting bigger, then it won't approach a number. And we call that diverging. So you can actually just look at series and tell that. So that one, for example, because it's shrinking over time, getting smaller and smaller numbers, it converges to 1. This one, although it's finite, it will converge to 75. But if it were infinite, 30 dot dot dot, it would go to infinity. That's called diverging. So again, series can be finite or infinite. If they're finite, you can always add them up because they end. If they're infinite, you can add them up as long as they converge. In other words, they get smaller as you go on. You cannot add them up if they diverge. Okay, that's it for our introduction to sequence and series. Now I'm going to do a couple other notations which we're going to use throughout this section of the class, which is the first one we're going to do is factorials. And we're going to use those in the context of sequence and series, but they're actually generally used for lots of other things, including probability, which some of you had, if you're doing this from the college algebra class, you had it last year. If you're doing algebra 2, you'll have it next. We're going to start with factorials, and then we're also going to cover summation notation. Let me start with factorials. What a factorial is, it's easier to show it just with numbers rather than an equation. If I have 6, first of all, the factorial symbol is an exclamation point, a very excited 6. This 6 factorial, this is called 6 factorial. This 6 factorial means it is 6, the first number of that, times 5, and you keep dropping 1, times 4, times 3, times 2, times 1, and you stop at 1. You can only do this for whole numbers, factorials. So for example, 98 factorial would be 98 times 97 times 96 times 95, and this goes a long ways. And the last one would be times 3 times 2 times 1. So that's a factorial. There's in your presentation, there's actually the definition which has it with ends and things like this, but I think this is a little easier to understand. The reason we do this is you saw earlier, like when the equations for sine and e to the x, they all had factorials in them, so they're commonly used in sequences and series. So let me give you an example of a sequence series with this. I'll do one out and then I'll have you do a couple. So let's say I have an explicit formula for a sequence that looks like this. Oops, that's supposed to be an n. A to the n equals n squared over n factorial. So I'm going to write the first 4 terms. A to the 1 is 1 squared over 1 factorial. 1 factorial is just simply 1. It's starting at 1 and going down to 1, which is just 1. So this is 1 squared over 1, or 1 over 1, or 1. A2 is 2 squared over 2 factorial, which is 4 over 2 times 1. 2 factorial is 2 until you get down to 1. So this is 4 over 2, or 2. A to 3, a sub 3 is 3 squared over 3 factorial, which is 9 over 3 times 2 times 1, which is, what is that, 9/6 or 3/2. And a 4, I'll do one more, is 4 squared over 4 factorial, which is 16 over 4 times 3 times 2 times 1. I should do a little cancellation here to simplify. That's 4 times 2 is 8. Over 16 over 8 is 2, so that's just 2/3. And a to the 5, for example, is 5 squared over 5 factorial, 25 over 5 times 4 times 3 times 2 times 1. That's a mess. 5, cancel that with that. 5 over, what is that left, 24? I think so, 5/24. Anyway, that's an example of using factorials in the context of sequences. Okay, and I'm going to have you try one. I'm going to write another explicit formula. A to the n equals 1 over n plus 1 factorial. And I'm going to write you, let's say, write the first 4 terms. Okay, pause the video there and try that one on your boards of paper, program boards. Okay, if you're back, I will do it and show you the answer. A to the 1 is 1 over 1 plus 1, which is 2 factorial, or 1/2. This is 2 times 1. A2 is 1 over 3 factorial, which is 1 over 3 times 2 times 1, or 1/6. A3 is 1 over 3 plus 1 factorial, which is 4 factorial, over 1 over 4 times 3 times 2 times 1. That's 24, so 1/24. We put some big numbers on here. A to the 4 equals 1 over 5 factorial, which is 1 over 5 times 4 times 3 times 1, which I know is 24. So that's 120. I'm not going to do another one because that's getting pretty big. Okay, we'll try one more. And yeah, let's try another idea with factorials. So I want you to do 16 factorial over 2 factorial times 14 factorial. I shall do one with you first. This is, by the way, called a combination. We'll do that when we do probability. It looks like it's a huge mess, and you can certainly do it with a calculator. But you also can just write this as 16 times 15 times 14, and I can stop there and put factorial. Because it's true this is 14 times all the way down to 1, but I don't need to do that. Because now I have 14 factorial at the bottom. And I can cancel those. This is 2 times 1. So those cancel. And I just get, I'm going to cancel that as well, 8 over 16 over 2 is 8 over 1. So 8 times 50 is 120, I believe. Yes, 120. Okay, let me have you try one of those. 9 factorial over 7 factorial. Pause the video there and try that one. Okay, if you're back, I can write this as 9 times 8 times 7 factorial over 7 factorial. Those cancel, so it's just 9 times 8, or 72. Again, this will come in handy when we use these for probability. Okay, last thing we're going to do is summation notation. So this is a new section in notes. Summation notation. And this is how a lot of sequences and series are written. Are written. And I'm going to write the notation first. This will look strange for the Algebra 2 people watching this, but college algebra, you had this last year. So here's the summation notation. You write a big S, which is the, this is the Greek capital S. It stands for sum. This means start at 1, go to some value, I don't know, 20, of some series. And you read it as the sum, that's this S, the sum of A sub k as k goes from 1 to n. That's the notation. So it's just a shorthand way of saying I start at 1, get A1, then I go 2, 3, 4, 5, 6, 7, 8, plus 2, plus A3, plus A4, etc., until I get to my last number, which is n. If this is infinity, which it can be, you just keep going until you say dot, dot, dot. This is what this means. That's called summation notation. I'll give you some examples. I'm going to have you do a couple. Let's do one here. Again, write down the examples in your notes so you can have something better than just that notation. That's a 5. Okay, this means start at 1, put it in your function over there, which is 3 times k. So 3 times 1 is 3. Then I put in 2. 3 times 2 is 6. Then I put in 3. 3 times 3 is 9. Then I put in 4. 3 times 4 is 12. Then I put in 4. 3 times 4 is, oops, 3 times 5 I put in, sorry, 15. And then this means sum them up, which is why I put the plus, 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 plus there. This actually has a value. It's not just this. It is actually what the sum of this is. So this is 3 plus 6 is 9, plus 9 is 18, plus 12 is 30, plus 15 is 45. There we go. And why do we write this? Because this is easier to write than a bunch of numbers written out in a giant series. So it's just a shorthand way of writing it, and it's commonly used. Let me give another one. And now I'll have you do a few. They don't have to start at 1, so I'm going to start this one at 5, and go to 8 of k squared. Okay, so the first term is just 5 squared, which is 25. Then add it, that means the sum. Second squared is 6, put 6 in. I'm going 5, 6, 7, 8. Put 6 in, I get 6 squared. Then put 7 in, I get 7 squared. Then put 8 in, I get 8 squared. There we go. That's my sum. That's a bit painful to add, but that's 149 plus 25, which is 174. There we go. Again, a shorthand notation of writing that. Okay, I'm going to have you do a couple now. I equals 1 to 4 of 2i squared. Okay, again, you're just looking for a single number at the end. Put this out as the terms there, and then add them up. Okay, pause the video and try that. Okay, so here's what you should do. You should put 1 in, and you get 2 times 1 squared. Actually, I'll write it out just so you can see it. Plus 2 times 2 squared, plus 2 times 3 squared, plus 2 times 4 squared. That's just putting the 1, the 2, the 3, and the 4 in pair from 1, 2, 3, 4 all the way up to there. So this is 2 plus 2 squared is 4 times 2 is 8. 3 squared is 9 plus 2 is 18 times 2, sorry. 4 squared is 16 times 2 is 32. And that equals 50 plus 10 is 60. There's my answer. Okay, I'm going to do one more. This one I'm going to do for you, just because it's a little weirder notation that you're probably not used to. I equals 1 to 4 of negative 1 to the I plus 1 power over I plus 1 factorial. So again, I've got 4 terms I'm adding up. I'm going to put them out here explicitly. I'm going to put negative 1. I'm going to start with 1. So that's I plus 1 is 2. By the way, notice I used I here. You use K, you use any variable you want. Typically, they're used either K, I, or N, but you can use anything. So I'm going to put negative 1 to the 1 plus 1, which is 2 squared, over 1 plus 1, 2 factorial. And I'm going to put 2 in. Negative 1 to the 2 plus 1, which is cubed, over 2 plus 1, which is 3 factorial. It's negative 1 to the 4th, over 4 factorial, starts with the pattern, plus negative 1 to the 5th, over 5 factorial. Notice what this does. Negative 1 squared is 1, negative 1 cubed is negative 1, negative 1 to the 4th is 1, negative 1 to the 5th is negative 1. This little thing in the front here, which is commonly used, allows you to alternate positive and negatives, which the sign function up front, if you remember, had in it, that alternating positives and negatives, and so did pi. So this is commonly written into the notation. So now I'll just write it out. This is 1 over 2 factorial, which is 2 times 1, or 1/2. This is negative 1 over 3 factorial, which is 6, 3 times 2, which is negative 1/6. This is 1, now positive, over 4 factorial, which is 4 times 3 times 2 times 1, which is 24. And then this is, the last one is negative 1 to the 5th, which is negative 1 over 5 times 4 times 3 times 2 times 1, which is 1/20th. Plus a negative. This will be minus 1/120th. That's a bit of a pain to combine, but as a common denominator, 120. So I can make this 60 over 120 minus 20 over 120 plus 5 over 120 minus 1 over 120. Or 60 minus 20 is 40, plus 5 is 45, minus 1 is 44 over 120. There we go. That's pretty awful. The things I do want you to take out of this is, though, this is a common notation, this negative 1 to the I plus 1, to give it alternating negative and positive signs. And also know what the function notation is, or the factorial notation is. Okay, that's it. So again, what we went through, just to sum up, sequences and series, first of all, are used commonly for getting constants, doing things in your calculator, like e to the x or sine x, and approximating things for physics equations. There are 2 ways to write them. You can write an explicit formula, which allows you to just put in 10th term and find the actual number, or a recursive formula, which needs the other terms before it to use it. And then finally, we reviewed factorial, which is right in here, which is just a number times the number below it times the number below it until you get to 1. And summation notation, which is just a shorthand way of writing series. That's it. The homework for those of you in college algebra is homework number 25, I believe, and for algebra 2 is homework number 16. Thanks, until next time.